Welcome to NovaSleep. What if everything we call nothing was the most powerful thing that exists? Tonight, we'll journey into the silent heart of the universe, the space between stars, between atoms, or even between thoughts, and discover that it isn't empty at all. Beneath the quiet, the vacuum seethes with invisible storms of creation, fields that never rest, energy that cannot die. The deeper we look into the void, the more alive it becomes, a hidden engine driving every photon, every force, every heartbeat in the cosmos. Stay with this thought as you drift deeper. The space around you, the stillness you feel, may be the most active place in the universe. By the end of this night, nothing will never mean the same again. By the way, if you like and subscribe to my video, this is the most effective way to support me. If you can tell me where in the world you're watching from and what time it is, I would love to read it in the comments. 1. The vacuum is a restless quantum ocean. When early scientists spoke of emptiness, they imagined a void, a featureless background where nothing existed and nothing ever happened. But the deeper our instruments probed, the clearer it became that emptiness is not absence, but presence in its purest form. What appears to be still and silent is actually the most active part of reality, a churning ocean of unseen fluctuations that never stop moving. Beneath every atom, beneath every photon of light, beneath every breath of air, the quantum vacuum surges like an infinite tide. It is a field that cannot rest, a rhythm that cannot be silenced. The particles that make up the world are merely waves upon this sea. They rise, crest, and fade back into it, transient formations born out of an eternal background hum. Nothing truly stands apart from it, not even time itself. The vacuum links every point in space to every other, weaving a network of energy so fine and so fundamental that without it, the universe would collapse into mathematical impossibility. If our eyes could somehow perceive the true nature of empty space, we would see a storm more violent than any star. Virtual particles would appear and vanish, pairs of opposites springing into being for unimaginably brief instants, borrowing energy from nowhere and giving it back again. The quiet we assume around us is only an illusion born from our slow perception. In truth, the universe is never still. This is why physicists no longer speak of a void but of the quantum field, the restless ocean that underlies all things. Its waves are subtle yet absolute, and from their interference the fabric of existence takes shape. Space is not where things happen, it is the thing that happens. 2. Zero-point energy remains even at absolute zero. The coldest temperature in the universe is not zero, it is a whisper above it. Absolute is up to zero. That mythical point where all motion should stop does not exist in nature. Even when matter is drained of every trace of heat, when its atoms are locked motionless in crystalline order, quantum mechanics refuses to let the story end there. The uncertainty principle demands that position and momentum can never both be known precisely, and so the particles must still quiver, faintly, unendingly. That irreducible vibration is zero-point energy, the heartbeat of a cosmos that cannot be silenced. In laboratories, scientists have chilled atoms to billionths of a degree above absolute zero. They expected stillness. Instead, they found motion. It was not heat. It was the raw tremor of existence itself, a movement with no cause but the laws of physics. This energy cannot be extracted, cannot be cooled away, and cannot be shut off. It is built into the blueprint of space and time. That invisible residue has profound consequences. It pushes against the boundaries of the universe, defines the baseline of all forces, and sets a limit beneath which energy can never fall. Even in the emptiest vacuum imaginable, the field persists, oscillating without source or sustenance. This means that nothing is never truly nothing. Even in the deepest silence, energy remains. This small and stubborn flicker of motion may be the reason why galaxies expand instead of collapsing, why the universe breathes outward instead of inward. Zero-point energy is the hum of existence when all else has been stripped away, the last note of creation, still echoing through eternity. 3. Quantum fields exist everywhere without interruption. Everything we see and touch, every atom, every grain of dust, every beam of light, is a ripple on a set of invisible fields that fill all of space. These fields do not turn off when the universe empties. They are the universe. Each fundamental particle, the electron, the photon, the quark, corresponds to a field that stretches across the entire cosmos. What we perceive as a single particle is simply a localized vibration in one of these universal fields. There is no point in the void where they do not exist. This continuity explains why the vacuum is never truly empty. Even when all visible matter is gone, the fields remain vibrating at their lowest possible energy. They overlap, interfere, and resonate, forming an invisible architecture that supports the visible world. Space is not an inert background, but a living fabric composed of these interconnected fields. The motion of one part subtly influences another, creating the harmony that gives rise to everything from atoms to galaxies. The presence of these fields has been proven countless times. When two plates are placed close together in a vacuum, they feel a gentle force, the Casimir effect, caused by the pressure of field fluctuations between them. When light interacts with electrons, its strength is slightly altered because the vacuum itself polarizes around them. Even the energy levels of hydrogen atoms shift by minute amounts due to these omnipresent fields. Every experiment whispers the same truth. The vacuum is not the absence of matter, but the stage from which matter emerges. The more we understand these quantum fields, the less separate we feel from the cosmos. Every heartbeat, every thought, every spark of light is an expression of the same underlying reality. One continuous field flowing through everything, connecting all existence in a single, unbroken wave. 4. The uncertainty principle forbids complete stillness. In the macroscopic world, we believe that something can be perfectly still, a rock resting on the ground, a pendulum at equilibrium, a planet frozen in orbit. But at the quantum scale, stillness is impossible. The uncertainty principle states that we cannot know both the position and momentum of a particle with infinite accuracy. The more tightly we pin one down, the more wildly the other fluctuates. As a result, every particle in existence is in motion, however subtle. This principle is not a limitation of measurement, it is a feature of reality. The universe is built on indeterminacy. Every atom vibrates, every electron buzzes with the impossibility of silence. When we imagine a perfect vacuum, devoid of particles, devoid of heat, this rule ensures that even then fluctuations remain. They cannot be removed because the fabric of the cosmos is woven from uncertainty itself. The consequences ripple through every layer of physics. The uncertainty in energy over short timescales allows virtual particles to appear and vanish, borrowing existence for brief instants before dissolving back into the void. It is this constant jitter, this infinite game of quantum hide and seek, that gives the vacuum its vitality. Even in apparent emptiness, the universe cannot help but create. Absolute stillness, it turns out, would violate the very logic of being. The cosmos survives because it refuses to settle. The vacuum trembles not from imperfection but from necessity, a perpetual vibration that ensures existence can never truly end. 5. Virtual particles flicker into existence and vanish again. Imagine a world where things appear from nothing and then vanish before they can be caught. A world where creation and annihilation happen endlessly, invisibly, right beneath your fingertips. That is not science fiction, that is the quantum vacuum. Within it, pairs of particles and antiparticles constantly appear, live for unimaginably brief moments, and annihilate each other, leaving behind a subtle trace of their passing. This process violates our everyday sense of conservation, yet it perfectly obeys quantum law. Thanks to the uncertainty principle, energy can be borrowed from nothingness as long as it is repaid quickly enough. These fleeting entities, called virtual particles, are not directly observable, but their effects are measurable. They slightly alter the charge of electrons, influence the strength of magnetic fields, and even contribute to the expansion of the universe. Each instant, everywhere, this phenomenon repeats itself. Appearance, interaction, disappearance. The vacuum boils with activity, even though we perceive calm. The very forces that hold atoms together, electromagnetism, the strong nuclear force, are shaped by the exchange of these temporary quanta. Without them, the structure of matter would disintegrate. When you look into the night sky, the space between stars seems empty. In reality, it's seething with ephemeral flashes of creation, the pulse of the quantum sea. Every cubic centimetre of space contains countless births and deaths per second, the invisible heartbeat of the universe itself. 6. The Casimir effect proves that emptiness can push. There is a strange experiment where two metal plates placed just nanometers apart in a perfect vacuum begin to move toward each other, not because of static, not because of air pressure, but because the vacuum itself is pushing them. This is the Casimir effect, one of the most haunting proofs that empty space is alive with energy. Between the plates, certain wavelengths of the vacuum field cannot exist, while outside them all wavelengths can. This imbalance creates a pressure difference, like the suction between two hands pressing together underwater. The result is a measurable force, tiny but undeniably real. It means that the vacuum exerts influence even when no particles, photons, or matter are present. The Casimir effect has been verified in laboratories countless times. It influences the design of nanomachines, alters how tiny mirrors vibrate, and sets fundamental limits on precision measurements. Yet beyond its technological relevance, it carries a profound philosophical message. The universe never fully rests. Even between two perfect mirrors, even in the purest void we can create, the hum of creation remains. The experiment transformed our concept of nothing. What once was the symbol of emptiness became a source of motion, pressure, and power. The vacuum, it seems, refuses to be silent. It insists on being felt. 7. Two mirrors close together feel the pressure of nothing. When two polished surfaces are brought incredibly close, separated by just a few hundred atoms, they begin to attract each other without touching. No light passes between them, no heat radiates, no particle moves. Yet somehow there is a force. That invisible hand is the pressure of the vacuum itself. Inside the narrow gap, the possible wavelengths of quantum fields are restricted, only certain modes can exist. Outside there are more. The imbalance creates a net inward push, as though the mirrors were being pressed together by invisible waves of nothing. This isn't metaphysical poetry, it's a measurable, repeatable fact of nature. Instruments can detect this push, and engineers must even account for it when building sensitive, nanoscale devices. The beauty of this phenomenon lies in its simplicity. It shows that space is never neutral. The vacuum behaves like an ocean that presses against everything it touches, not with friction, but with the delicate insistence of its own structure. The mirrors don't move because of magic, they move because the fabric of space between them is thinner than the fabric outside. The force is tiny, yet its meaning is immense. It reminds us that the universe is not built upon emptiness, but upon balance. Wherever that balance is disturbed, even slightly, the vacuum itself moves to restore it. That is the quiet power of nothing. 8. The Lamb shift reveals that even atomic energy levels are moved by the vacuum. In the early days of quantum theory, scientists believed that the energy levels inside an atom were exact and unchanging, pristine mathematical steps rising from the nucleus outward. But in 1947, a quiet experiment overturned that certainty. Physicist Willis Lamb measured the energy of hydrogen's electron and found a small, inexplicable difference. The levels were not where theory said they should be. The discrepancy was minuscule but real, and it came not from the atom itself, but from the vacuum surrounding it. The discovery revealed that the empty space around an electron is not neutral. Virtual particles in the vacuum constantly pop into existence and vanish, subtly distorting the electromagnetic field around the atom. These fluctuations shift the energy of the electron just enough to make the spectrum wobble, like the trembling reflection of a coin seen under rippling water. It was the first clear proof that the vacuum desperately changes matter, that even at the smallest scales, nothing leaves its fingerprint on something. The Lamb shift forced physics to evolve. The neat equations of early quantum mechanics gave way to the richer language of quantum electrodynamics, where particles and fields interact endlessly through the medium of vacuum fluctuations. This theory became the foundation of modern physics, and its predictions match experiment to astonishing precision. The tiny deviation that Lamb found was the first whisper of this deeper truth. Every atom, every chemical bond, every piece of light we see carries the subtle correction of that same vacuum. Even when we think we are measuring matter, we are also measuring the invisible energy that surrounds it. The vacuum is not background noise, it's part of the music itself. 9. Electric charge is slightly screened by the polarization of empty space. At first glance, an electric charge seems simple, a fundamental property that repels or attracts other charges according to distance. But quantum field theory paints a more intricate picture. Surrounding every charged particle is a halo of virtual particles drawn from the vacuum itself. Pairs of virtual electrons and positrons flicker in and out of being, orienting themselves around the charge much like iron filings align in a magnetic field. The result is that the raw charge becomes slightly screened, muted by its own echo in the vacuum. This means that what we call an electron's charge isn't a single isolated value, but a dynamic effect shaped by constant interaction with nothingness. At very close distances, where the screening cloud cannot form, the charge appears stronger. Farther away, it appears weaker. In a sense, the vacuum behaves like a transparent medium that bends and softens the field lines of the electron, hiding its full intensity behind layers of self-generated energy. This phenomenon is known as vacuum polarization, and it has measurable consequences. It subtly alters how light scatters, how atoms bond, and how particles behave inside accelerators. It's not something we can see directly, but without it, the mathematics of quantum electrodynamics would fail. The fact that empty space behaves like a polarizable material like glass or water, but infinitely more subtle, transforms our understanding of the cosmos. Even charge itself turns out to be a conversation between the particle and the vacuum that cradles it. Space does not merely allow forces to pass through it, it shapes them, filters them, and in doing so becomes one of the most active participants in nature. 10. The electromagnetic field can never fully shut down. We are taught that when the lights go out, when power lines go silent, and when charges rest, the electromagnetic field vanishes. But at the quantum level, the field never truly stops. Even in perfect darkness, even at absolute zero, electromagnetic oscillations continue to flicker throughout space. The field exists whether or not there are photons traveling within it. It is a permanent presence, a vibrating lattice of potential. This eternal hum gives rise to what we call vacuum fluctuations, spontaneous random oscillations in the electromagnetic field that appear even when there are no sources. These fluctuations are not errors in measurement or noise from the environment. They are the inevitable result of quantum mechanics applied to the field itself. Just as a guitar string cannot be held perfectly still, the field that fills the universe cannot be made motionless. It resonates at every possible frequency, though most of those tones are hidden beneath the limits of detection. This constant background gives birth to extraordinary effects. It shifts the orbits of electrons, generates subtle pressures between metal surfaces, and even influences the propagation of light across cosmic distances. Every beam of starlight passing through interstellar space rides upon this vibrating ocean, ever so slightly shaped by it. The universe's silence is alive with invisible motion. The persistence of the electromagnetic field means that nothing can ever be truly turned off. Energy remains, waiting, not stored like fuel, but embedded in the very structure of existence. Even when we believe we have found stillness, the field continues to sing, softly and forever. 11. Light moves not through emptiness, but through a trembling background. To our eyes, the path of a photon appears effortless, a straight line across the void, unimpeded, pure. But in reality, light does not glide through emptiness. It travels through a quantum fabric in constant turmoil. Every photon's journey is a conversation with the restless vacuum beneath it. As it moves, it interacts with virtual particles and temporary distortions of the electromagnetic field, like a surfer gliding across waves too small to see. The vacuum, far from being empty, has a texture. It is a medium in which even light feels friction, though so faintly that it takes heroic precision to detect. Quantum corrections subtly alter how light propagates, how fast it travels, and even how it bends around massive objects. In extreme conditions, near black holes or within powerful magnetic fields, the vacuum itself behaves like glass, polarizing and refracting the light that passes through it. This trembling background is not a hindrance but a necessity. It allows light to exist as both wave and particle, as disturbance and object. The photon is born from oscillations in the electromagnetic field, which in turn are sustained by the energy of the vacuum. Without that background, there would be no light at all. The interplay between photon and vacuum defines not only the behavior of light, but the very meaning of space. So when you imagine a beam of light crossing the galaxy, remember that it's never truly alone. It moves through a sea of unseen waves, a field of infinite energy and eternal motion through which the universe whispers to itself in the language of light. 12. Space itself is an active participant in every experiment. In classical science, space was a passive backdrop, a stage upon which the actors of matter and energy performed. Today we know that this picture is wrong. Space itself takes part in every interaction. It stretches, vibrates, polarizes and responds. When particles move, the vacuum around them shifts. When fields change, space adjusts its structure to accommodate them. Every experiment, no matter how controlled, includes an unseen collaborator, the vacuum field that underlies reality. This participation is not metaphorical. In particle accelerators, detectors record events that cannot be explained unless we account for the vacuum's input. In quantum optics labs, photons behave differently depending on how we shape the empty space around them. The geometry of space, the boundaries of mirrors, even the presence of nearby fields all change how nothing behaves. What we call an experiment on matter is always, in truth, an experiment on the vacuum. The realization that space is active reshapes physics at every level. Gravity curves it, quantum fields fill it, and energy flows through it like current through a living wire. To speak of particles moving through space is misleading. Particles are localized vibrations of space. What we move through is not emptiness, but a fabric alive with potential. Every act of observation touches this living background. Each measurement, each collision, each burst of energy sends ripples through the silent participant we call space. The universe is not performed upon a stage. It is the stage itself, forever shifting under its own performance. 13. Every particle is a ripple in a universal field. If you strip away the metaphors and the mathematics, one truth remains: particles do not exist as standalone entities. They are localized excitations, ripples, in the fundamental fields that fill the cosmos. An electron is a vibration of the electron field, a photon a vibration of the electromagnetic field, a quark a vibration of the quark field. Each type of matter and force corresponds to its own invisible sea, and all of them coexist, layered together in the same expanse of space. This means that the universe is not built from particles like a child's toy box, but from patterns of vibration. When two electrons repel each other, they do so not because invisible marbles bounce between them, but because their ripples interfere through the shared field they inhabit. The world we see, solid, colourful, textured, is an illusion woven from waves. This view is more than poetic. It explains why particles can transform into one another, why energy and matter are interchangeable, and why the laws of physics are the same everywhere. The fields are the reality. The particles are the fleeting shapes those fields take when disturbed. Every bit of matter is part of a single cosmic ocean. The boundaries we perceive are temporary ripples separating one form of vibration from another. When those ripples fade, what remains is the calm but infinite field that has always been there. The true face of the vacuum. 14. Mass arises from the interaction between matter and background fields. The concept of mass once seemed simple, an intrinsic property, a measure of how much stuff an object contained. But modern physics reveals a deeper story. Most of what we call mass is not a static quantity at all. It's the result of interaction with the invisible background fields of the universe. The most famous of these is the Higgs field, pervasive energy field that fills all space. According to the standard model of physics, particles that interact as strongly with the Higgs field gain mass, while those that barely interact move freely, almost massless. It's as though the field acts like a cosmic molasses, slowing some particles while letting others glide through untouched. Without this interaction, matter as we know it could not exist, and atoms would not form, stars could not ignite, and the universe would remain a shapeless blur of radiation. But the Higgs field is not alone. Quantum chromodynamics, the theory of the strong force, tells us that even the protons and neutrons in atomic nuclei derive most of their mass, not from their constituent quarks, but from the energy of the vacuum fields binding them together. Mass is not something an object has, it's something it experiences through interaction. This realization unites matter and space in a profound way. Mass is not imposed upon the vacuum, it emerges from it. Every solid thing you touch, every planet you see, is a manifestation of the invisible handshake between particles and the ever-present fields that fill the universe. 15. Inertia might be the echo of interaction with the vacuum. When you push an object, it resists. That resistance, inertia, has been known since antiquity, yet its origin remains one of physics' quiet mysteries. Some modern theories suggest that inertia itself may arise from the quantum vacuum. In this view, an accelerating particle interacts with the fields that fill empty space, and those interactions generate a kind of electromagnetic drag, a subtle resistance born not of friction but of quantum coupling. If true, this would mean that the feeling of mass, the weight of matter, and even the effort it takes to move are all echoes of the vacuum's invisible structure. As you push an object, you are, in a sense, pushing against the fabric of reality, against the zero-point field that fills every corner of existence. The energy required to accelerate anything would then be the cost of disturbing this field. Hints of this idea appear in the Unruh effect, which predicts that an accelerating observer sees the vacuum as a warm bath of particles, while an observer at rest sees none. Inertia might be the macroscopic face of the same phenomenon, a resistance caused by how motion changes the way we experience the vacuum. Though still speculative, the idea is intoxicating. It suggests that every act of motion, every spin of a wheel, every orbit of a planet is a dialogue with the invisible sea that underlies the cosmos. To move is to disturb the vacuum, and the vacuum in turn pushes back. 16 poles, so vacuum energy could be what fuels cosmic expansion. When astronomers looked into the deep night sky, they expected to see the expansion of the universe slowing down under the pull of gravity. Instead, they found something astonishing. The expansion is speeding up. Galaxies are drifting away from one another faster and faster, as though some unseen pressure were stretching the very fabric of space. That hidden pressure is what scientists now call vacuum energy, the energy of empty space itself. Unlike matter or radiation, which dilute as the universe grows, vacuum energy does not fade. It remains constant, pushing outward with the same relentless force no matter how vast the cosmos becomes. This means that the more space expands, the more vacuum there is, and thus the more energy pushing the universe apart. It's a feedback loop written into the structure of existence. The universe, it seems, expands because the vacuum demands it. This idea transforms emptiness from a passive void into a dynamic engine. The same energy that hums invisibly between atoms also propels galaxies apart. And the strange part is that this cosmic expansion does not require anything new. It arises naturally from the same quantum fluctuations that fill every corner of space. What we once thought of as nothing is, in truth, the most powerful something there is. If this interpretation is correct, then every second of cosmic acceleration, every widening of intergalactic distance is the signature of the vacuum itself breathing. The universe is not just moving through space, it is being moved by space. 17. The cosmological constant may simply be the pressure of the vacuum. When Albert Einstein first formulated general relativity, he added a term to his equations called the cosmological constant. He believed the universe was static, so he introduced this constant to counteract gravity's pull. Later, when astronomers discovered that the universe was expanding, Einstein regretted the addition, calling it his greatest blunder. But decades later, his blunder returned as one of the most profound truths in physics. The cosmological constant perfectly describes the effect of vacuum energy. It represents a uniform pressure that fills all of space, stretching it evenly in every direction. In modern terms, it's the mathematical face of the vacuum's push, the reason galaxies accelerate away from one another. Far from being an arbitrary patch, it may be the simplest expression of how nothingness behaves when translated into geometry. Yet there's a problem that still haunts physics. When we calculate the amount of vacuum energy predicted by quantum field theory, the number is absurdly large, about 10 to the power of 120 times greater than what we observe in the sky. Something somewhere cancels nearly all of it, leaving only a faint residue strong enough to shape the cosmos. Why the universe chose this delicate balance remains one of the greatest mysteries in science. Perhaps this balance is not an accident, but a clue that the geometry of space-time and the quantum fabric of the vacuum are two sides of the same coin. The cosmological constant may not be a tweak in the equation, but the signature of reality's most fundamental force, the quiet pressure of being itself. 18. Cosmic inflation began as a surge of vacuum energy. Long before stars, long before atoms, the universe may have been smaller than a grain of sand, and then, in an instant, it exploded in size by an unimaginable factor. This event, known as cosmic inflation, is believed to have been driven by vacuum energy. In those first fractions of a second, space itself expanded faster than the speed of light, not because matter was moving through space, but because space was stretching under the force of its own energy. The engine behind this expansion was a high-energy vacuum state, an unstable form of nothingness that released its energy in a burst of creation. When this vacuum decayed into a lower energy state, it left behind all the matter and radiation that would later form galaxies, stars, and life. In this sense, everything we see today, every planet, every atom, is the residue of that ancient vacuum transition. Inflation solved many cosmic puzzles at once. It explains why the universe appears flat, why distant regions look so similar, and why tiny fluctuations in the early vacuum grew into the vast structures we observe today. But it also raised new questions. What caused the inflationary vacuum to begin, and what caused it to stop? Could other bubbles of space still be inflating elsewhere, creating endless universes beyond our own? If so, then our universe may be just one ripple in an infinite sea of vacuum expansions, a single bubble rising from an eternal foam. The Big Bang might not have been the beginning of everything, but simply the beginning of our local chapter in an ongoing story of creation written in the language of the vacuum. 19 Perpetuos. Quantum tremors in the early vacuum seeded the galaxies. When cosmic inflation ended, the universe was left with faint irregularities, tiny fluctuations in density caused by the restless energy of the vacuum. These quantum ripples were infinitesimal, smaller than atomic nuclei. Yet as the universe expanded and cooled, they grew, drawing matter towards slightly denser regions until the first stars and galaxies emerged. In this way, every galaxy in the sky was born from a momentary tremor in the early vacuum. This link between the quantum and the cosmic is one of the most extraordinary connections in science. Random fluctuations in the subatomic fabric of space eventually shaped the grand architecture of the universe. The same laws that govern the jitter of electrons in an atom sculpted the distribution of galaxies across billions of light years. Every spiral galaxy, every cluster, every cosmic void is a magnified echo of quantum noise frozen into the geometry of space. The cosmic microwave background, faint radiation left from the early universe, still carries the imprint of these fluctuations. Tiny variations in its temperature are direct evidence of the vacuum's ancient pulse. Each pixel in that cosmic map tells a story billions of years old, written in the language of quantum randomness. It is humbling to realize that the grandest structures in existence began not with matter, but with the whisper of the vacuum itself. What we call the universe may just be the amplified vibration of an ancient invisible hum that never truly stopped. 20. Multiple vacuum states may exist with different physical laws. We often think of the laws of physics as absolute, unchanging universal truths. But some theories suggest that these laws depend on the vacuum itself. Just as water can exist as ice, liquid, or vapor, the vacuum may have multiple stable or metastable states, each with its own set of properties. In one vacuum, electrons might have a different mass. In another, light might travel at a different speed. In yet another, gravity itself might behave differently. This idea leads to a staggering possibility that our universe is just one region of a vast multiverse, each part locked into its own vacuum configuration, with its own physics. Between these regions might lie transitions, cosmic boundaries where one vacuum gives way to another, like the surface between phases of matter. We cannot yet observe such domains, but mathematically they are consistent with what we know about field theory and cosmic inflation. In this vision, the vacuum is not a single stable ground, but a landscape of possibilities. Our universe happened to settle into one valley among countless others, a region where the physical constants permit atoms, stars, and life. Elsewhere, conditions might be utterly alien, perhaps even inhospitable to structure itself. If true, this means that the vacuum is the ultimate author of reality. It decides the rules by which everything plays. The laws of nature, once thought fundamental, could instead be local customs of our particular patch of the cosmic field. 21. Our universe might be trapped in a false vacuum. If the vacuum can exist in multiple states, then not all of them are equally stable. Some are true vacua at all, the lowest possible energy states, while others are false vacua, local minima that appear stable, but are not the ultimate ground. There is a chance, however small, that our universe is currently trapped in one of these false vacua, resting on a plateau that could someday collapse into a deeper state. In that event, a tiny region of space could spontaneously tunnel into the lower energy vacuum, forming a bubble that would expand at nearly the speed of light, rewriting the laws of physics as it grew. Inside that bubble, atoms would not survive. Light and time themselves might behave differently. It would be the ultimate reset set of the universe, shedding its old rules for new ones, without warning, without pain, without toil. While this scenario sounds apocalyptic, it is also profoundly enlightening. It reminds us that stability is an illusion, that even the vacuum itself may only be temporary. The universe, so solid in appearance, could be a structure balanced on a thin layer of energy, poised delicately between existence and transformation. The thought is unsettling yet strangely beautiful. It shows that creation is not a one-time event but an ongoing process, that the vacuum itself may still be evolving, searching for its final, perfect form. 22. Vacuum decay could rewrite the laws of physics in an instant. If our universe truly occupies a false vacuum, then it lives on borrowed time. The decay of such a vacuum would begin at a single point, a microscopic bubble of lower energy space that would expand faster than light. Everything it touched would dissolve into a new reality governed by new constants, new particles, new geometry. There would be no explosion, no warning, only a silent transformation sweeping through the cosmos. Physicists have calculated that if such a decay were possible, it would happen spontaneously, requiring no external trigger. Quantum tunneling, the ability of particles to slip through energy barriers, applies to the vacuum itself. Fortunately, if the energy difference between vacua is small, the decay rate is unimaginably slow, making the universe safe for billions of years. Still, the possibility remains a haunting reminder that permanence is an illusion even at the deepest level of nature. This potential for sudden transformation highlights how delicately balanced reality is. The stability of the vacuum underpins everything: matter, forces, chemistry, even life. If it were to change, everything would change with it. Our atoms, our stars, our very notions of cause and effect would be rewritten in a single instant. Perhaps this fragility is not something to fear but to revere. The universe continues only because the vacuum allows it to. Each second of existence is an act of grace performed by the most fundamental energy there is, the one that cannot be seen yet sustains everything. 23. New bubbles of vacuum may have formed in the infant cosmos. During the universe's first fractions of a second, conditions were extreme enough for multiple vacuum transitions to occur. As the cosmos cooled and expanded, regions of space could have settled into different vacuum states, forming bubbles separated by thin boundaries of immense energy. Each bubble would have contained its own version of physical reality, expanding rapidly until it collided with others or drifted forever beyond causal contact. If this happened, then our observable universe might be just one bubble among countless others floating in the cosmic sea. Some bubbles might still be forming even now, beyond the horizon of our perception, endlessly budding off from inflationary space. This process, called eternal inflation, would mean that creation never truly stopped. It continues eternally, spawning new universes from the vacuum's inexhaustible potential. The collision between such bubbles could leave scars, subtle imprints in the cosmic microwave background or gravitational wave patterns stretching across the sky. Scientists search for these faint signals as clues to the vacuum's hidden history. So far, none have been confirmed, but the possibility remains tantalizing. If every bubble contains its own laws, its own time, its own definition of reality, then existence is far larger than we can imagine. What we call the universe may be only one cell in an infinite foam of creation, each formed from the same restless vacuum energy, each humming with its own rhythm of being. 24. The cosmic microwave background carries the fingerprints of the first vacuum. The oldest light in the universe, the cosmic microwave background, CMB, is not just a remnant of heat from the Big Bang. It's a fossil record of the vacuum's earliest vibrations. This faint glow, stretched into microwaves by billions of years of expansion, still carries tiny variations in temperature and polarization that mirror the quantum fluctuations present during cosmic inflation. Every slight ripple in that ancient radiation corresponds to a subtle difference in the density of the early universe, seeded by the vacuum's restless energy. These differences became the scaffolding upon which galaxies and clusters later formed. In this way, the CMB is both a photograph of the universe as a newborn and a portrait of the vacuum itself in its first visible act of creation. By studying these patterns, scientists have been able to measure the universe's age, shape, and composition with remarkable precision. The CMB tells us that the vacuum has a constant energy density, that space is nearly flat on cosmic scales, and that the same laws of physics hold everywhere we look. Yet it also hints at deeper mysteries, the possibility of multiple vacua, subtle anisotropies, and quantum features that our instruments have only begun to resolve. To look at the cosmic microwave background is to see the vacuum's first signature frozen in light. It is the universe remembering its own birth, the echo of nothingness becoming everything. 25. Dark energy could be the macroscopic face of vacuum energy. In 1998, astronomers studying distant supernovae discovered that the universe's expansion was accelerating. The simplest explanation was a new form of energy, one that permeates space uniformly and exerts negative pressure. They called it dark energy, and to this day its true nature remains a mystery. But many physicists suspect it is nothing more exotic than the quantum vacuum itself, manifesting on a cosmic scale. If vacuum energy is constant everywhere, its gravitational effect would be repulsive, driving galaxies apart. This perfectly matches what we observe. The density of dark energy remains nearly the same even as the universe grows, meaning that the more space there is, the more dark energy there becomes. It's a feedback of pure existence, a cosmic inflation stretched across eternity. If this is true, then dark energy is not a new substance, but an old truth made visible. The same restless zero-point field that vibrates within atoms also fills the void between galaxies. What seems cold and empty is, in fact, radiant with invisible energy, expanding the cosmos at an ever-increasing pace. The realization is both humbling and profound. The universe's acceleration, the future of its stars, even the ultimate fate of time itself, may all be governed by the same subtle force that animates every corner of space, the vacuum's eternal silent pulse. 26. Hawking radiation is born from the vacuum near black holes. At first glance, nothing could be more absolute than a black hole. Its gravity is so extreme that not even light can escape, sealing all information behind an event horizon. For decades, scientists believed that once something fell in, it was lost forever. But in 1974, Stephen Hawking made a discovery that shattered that idea. He realized that even black holes cannot sequence the quantum vacuum. At the edge of the event horizon, the vacuum's fluctuations continue, producing pairs of virtual particles, one falling into the black hole, the other escaping into space. The escaping particle becomes real, carrying away energy. Slowly, imperceptibly, the black hole radiates. This radiation, now known as Hawking radiation, reveals that black holes are not eternal. They evaporate over unimaginable timescales, leaking energy drawn from the very curvature of space-time. What seems like emptiness around the horizon is actually a cauldron of quantum activity, where gravity and quantum mechanics meet in an uneasy dance. The black hole becomes not a hole in space, but a glowing ember of the vacuum's endless creativity. The process unites two great theories that once seemed irreconcilable. General relativity describes the smooth geometry of space-time. Quantum field theory describes the restless sea of fluctuations within it. Near the event horizon, both collide. The vacuum there becomes distorted, stretched by gravity, creating a bridge between the micro and the cosmic. The black hole's glow is not fire in the traditional sense. It's geometry itself turning into light. Hawking's insight changed physics forever. It showed that even the universe's darkest places cannot suppress the vacuum's whisper. Emptiness, it turns out, always finds a way to speak, even through the silence of a black hole. 27. Gravity can tear apart virtual pairs and turn them into real particles. In the emptiness of space, virtual particles are constantly appearing and disappearing, always in pairs that cancel each other's existence. But near intense gravitational fields, this fragile balance breaks. One particle of the pair can fall deeper into the gravitational well, while its partner escapes, gaining energy from the field itself. The result is the creation of real particles from the vacuum powered by gravity's pull. This phenomenon is not just theoretical, it happens near black holes as Hawking radiation, but it may also occur in other extreme environments, around neutron stars during cosmic inflation, or wherever space-time stretches violently. Gravity in this view is not merely a geometric warping of space but a participant in the constant transformation of energy. It can pull the quantum fabric apart, turning virtual existence into tangible reality. The process demonstrates that mass and energy are not isolated currencies but interchangeable expressions of geometry. When gravity distorts space-time, it changes how the vacuum behaves. What was once balanced becomes asymmetric, and the imbalance becomes creation. Out of the curvature of nothing, something emerges. This concept bridges two worlds. It suggests that gravity, rather than being a separate force, may be an emergent phenomenon born from the vacuum's behavior itself. Every star, every burst of radiation, every gravitational wave could be a ripple in the same underlying field that produces particles out of empty space, the universe making itself from its own tension. 28. The event horizon marks the boundary between information and nothingness. To an outside observer, a black hole's event horizon looks like a perfect edge, a place where light halts, time slows, and the universe ends. But from the perspective of physics, it's far more subtle. The event horizon is not a solid surface, it's a boundary of knowledge, a line that separates what can be observed from what can never be retrieved. It is the horizon between the known and the unknowable, between something and the apparent nothing. At that invisible border, the quantum vacuum behaves differently. Virtual particles near the horizon experience immense tidal forces, stretching and splitting in ways that produce radiation and entropy. Information that falls toward the black hole becomes encoded in faint quantum imprints on the horizon's surface. This means that even though matter disappears beyond view, its informational essence might still remain, smeared across the boundary like ink on parchment. Physicists now suspect that the event horizon acts as a vast memory screen for the universe, holding every bit of data that enters it, albeit scrambled and distorted. The vacuum there becomes a carrier of information, storing it in subtle quantum correlations that persist even as the black hole evolves. Thus, the event horizon is not the end of reality but a threshold where information, energy, and geometry merge. It is the vacuum's way of keeping secrets, not by erasing them, but by folding them into its infinite complexity. 29. Black hole evaporation links gravity and quantum fields. Hawking's discovery of black hole radiation was more than a theoretical breakthrough. It was a revelation about the nature of reality. It proved that gravity and quantum physics, though born from separate frameworks, are deeply connected through the vacuum itself. When a black hole emits radiation, what's truly happening is an exchange between space-time curvature and quantum fields, geometry converting into particles, energy transforming into light. This process unites the universe's largest and smallest scales. The black hole, a product of gravitational collapse, interacts with the vacuum's quantum foam, and in that conversation, information and energy flow between them. Each particle of Hawking radiation is a message from the depths of curved space-time, a fragment of geometry turned physical. As the black hole radiates, it loses mass and shrinks, causing its temperature to rise. Over billions of years, it will evaporate completely, leaving behind nothing but a final burst of energy, the last echo of its interaction with the vacuum. What began as an object defined by gravity ends as a quantum process, a seamless handoff between two pillars of physics. This phenomenon suggests that space-time itself might be a quantum field, one whose fluctuations we perceive as gravity. The black hole is not an exception to the rules of the vacuum. It is their most dramatic stage, where emptiness and curvature dance until one becomes the other. 30. The entropy of a black hole points to hidden bits in the vacuum. When physicist Jacob Bekenstein proposed that black holes possess entropy, a measure of disorder, his peers were skeptical. How could something that swallows everything have a countable amount of information? But Hawking's radiation confirmed that black holes are thermodynamic objects. They have temperature, entropy, and energy. That realization carried a deeper implication. If a black hole has entropy, it must also have microstates, hidden configurations that encode its internal information. These microstates are thought to reside on the event horizon itself, stored not in matter but in the quantum structure of the vacuum. Every square patch of the horizon's surface corresponds to an enormous number of microscopic degrees of freedom. This means that space, far from being smooth, has a discrete information-bearing texture at the smallest scales, possibly at the Planck length. The discovery revolutionized our understanding of the vacuum. It implied that the geometry of space and the content of information are inseparable. Entropy, temperature, and information are not emergent properties of matter alone, but built into the vacuum's own design. In this view, a black hole is a lens into the true nature of reality. It tells us that emptiness stores data, that space remembers, and that the vacuum's silence is filled with the murmurs of all that has ever fallen into it. By the way, if you like and subscribe to my video, this is the most effective way to support me. 31. Entanglement may form through the underlying vacuum field. Quantum entanglement, the mysterious connection between particles separated by vast distances, is one of the strangest features of physics. But what if the medium that allows it isn't invisible threads or faster than light signals, but the vacuum itself? In this interpretation, entangled particles are not communicating across space, they are sharing a single quantum field that spans them both. Because all particles arise from underlying fields, two particles that were once part of the same wave remain linked through the vacuum fluctuations that gave them birth. This means their correlation is not a signal sent between them, but a property of the field that connects them. The vacuum, therefore, is not a passive emptiness, but a web of relationships, a universal field where separation is an illusion. This view solves some of the paradoxes of entanglement. The particles do not need to talk faster than light, because they never truly parted. The vacuum's continuity ensures their connection, even across cosmic distances. When one particle is measured, the state of the field adjusts globally, updating the entire system at once. Entanglement thus reveals a profound truth. Space is not empty, and objects are not truly isolated. Every particle, every atom, every living being is woven into the same invisible fabric. The vacuum is the unseen unity beneath the apparent diversity of the cosmos. 32. Space-time geometry could emerge from patterns of entanglement. Einstein showed that gravity is the curvature of space-time, but modern physics hints at something deeper, that this curvature may itself arise from quantum entanglement. The idea is breathtaking. The smooth geometry of space could be an emergent phenomenon, built from the complex web of quantum correlations encoded in the vacuum. In this framework, space-time is not fundamental but relational. The distances between points, the flow of time, and even the concept of locality all emerge from how quantum states are connected. The more entangled a region of space is with its surroundings, the more robust and continuous its geometry becomes. Where entanglement fades, space itself begins to fragment, as though reality dissolves when the connections within the vacuum weaken. This radical perspective unites quantum theory and gravity in a new way. Instead of viewing space as the stage and particles as the actors, we see both as manifestations of a deeper information network, a self-organizing system built from the vacuum's entangled microstates. Geometry is what entanglement looks like when seen from a distance. If true, this means that the entire cosmos is a projection of relationships woven through the vacuum, a holographic web where gravity, matter, and space are all emergent patterns in the same underlying code. The universe is not made of things, it's made of connections. 33. The holographic principle treats the universe as information on a boundary. Imagine if everything that exists, every galaxy, every atom, every thought, could be described by information stored on a distant surface. This is not fantasy, it's the holographic principle, a bold idea suggesting that the entire three-dimensional universe is a projection from information encoded on its boundary. The inspiration came from black hole physics, where the entropy of a black hole is proportional not to its volume, but to the area of its event horizon. If the vacuum itself follows this rule, then space as we know it is a hologram, a detailed image woven from the information stored on the cosmic horizon. The interior of the universe, including us, would be a manifestation of data processed within the vacuum's quantum fabric. This doesn't make reality an illusion. It means that the essence of existence is informational rather than material. This principle provides a framework that could unify quantum mechanics and gravity. If information is conserved on the boundaries of space-time, then nothing is ever truly lost, even when swallowed by black holes. The vacuum becomes both the storage medium and the processor of the universe's data. In this sense, the cosmos may be the ultimate holographic projection, one in which the quantum vacuum is both the film and the light that illuminates it. Every moment we experience, Every particle we detect could be a pixel in the great hologram of existence. 34 semusins. Vacuum fluctuations might preserve correlations across time. The vacuum is not only active in space, it is also alive in time. Quantum fluctuations occur everywhere and everywhen, linking events across the past, present, and future through subtle correlations. These are not messages or signals, but threads of probability that tie the timeline of the universe together. The vacuum's fluctuations ensure that every event leaves a faint echo, a memory that persists in the statistical structure of reality. This temporal entanglement means that what we do now is influenced, however slightly, by the ripples of past fluctuations, and in turn our actions send faint imprints forward. Time, therefore, is not a river flowing one way, but a fabric continuously rewoven by the vacuum's vibrations. The present moment is a region of interference where the waves of past and future meet. Some physicists suspect that this hidden continuity may explain quantum coherence, memory effects in particles, and even the subtle order seen in chaotic systems. The vacuum, through its constant fluctuation, might carry the seeds of causality itself. If this is true, then time is not a one-way path, but a resonance pattern, sustained by the vacuum's eternal motion. Every second we live is balanced delicately on the edge of this unseen rhythm, the music of the universe played in silence. 35. The fabric of space could hold quantum memory. When we think of memory, we imagine neurons, computers, or records, systems designed to store information. But what if memory is a property of space itself? Quantum theory suggests that every interaction, every collision, every fluctuation leaves a trace in the vacuum, encoded in subtle correlations among its fields. This means that space is not a blank canvas, but a repository of everything that has ever happened within it. These imprints are not classical memories. They cannot be read directly, but they manifest statistically, influencing the probabilities of future events. The vacuum remembers through entanglement, through the way its fluctuations remain correlated long after an interaction ends. Information once created cannot be erased. It can only be redistributed. This concept gives new meaning to the conservation of information. Even when particles annihilate or energy radiates away, the vacuum retains the record in its structure. In a sense, every point in space is a tiny library of the universe's history, written in the language of quantum fields. To grasp this idea is to see space as something alive, so not conscious, but responsive, layered, and self-aware in its physics. The vacuum is not forgetful emptiness, it is the ultimate memory, the silent archive of everything that has ever been. 36. Symmetry breaking in the vacuum brings particles into being. In the earliest moments of the universe, the vacuum was perfectly symmetrical, a uniform state without distinctions, without masses, without form. But perfect symmetry is unstable. Like a pencil balanced on its tip, it can persist only until the slightest fluctuation knocks it into a new configuration. That tiny imbalance shattered the pristine uniformity of the primordial vacuum and gave birth to everything we know. This process is called spontaneous symmetry breaking, and it is the heartbeat of creation. When the vacuum symmetry broke, fields that once held equal value diverged. The Higgs field, for example, acquired a non-zero average value, filling space with a new kind of energy landscape. Particles moving through it began to interact with this field, and through that interaction, they gained mass. The universe went from a formless energy soup to a structured system filled with diverse particles and forces. From the stillness of perfect symmetry, complexity and individuality emerged. This process didn't happen just once. It may have occurred multiple times as the universe cooled. Each symmetry breaking changed the rules of physics slightly, locking in new constants and interactions. The world we inhabit is the residue of those frozen choices. Every proton, every atom, every star is a fossil of those ancient transitions. In the language of the vacuum, creation is not an explosion but a reorganization. The universe became rich and diverse, not because something was added, but because the vacuum decided to tilt, and in that tilt, reality unfolded. 37. Matter might simply be frozen vibrations of the vacuum. We often imagine matter as something fundamentally solid, composed of tiny building blocks. Yet quantum field theory reveals a far more fluid truth. Matter is a stable pattern of vibration in the vacuum itself. An electron, for instance, is not a miniature sphere whizzing around an atom. It's a localized oscillation of the electron field, a standing wave that persists because of the field's properties. Every particle in the universe is a similar pattern, so a ripple frozen into form. The vacuum is the orchestra, and matter is the music, momentarily crystallized into notes we can perceive. The persistence of these vibrations gives rise to what we call solidity, but beneath that illusion lies constant motion. Even a rock at rest is composed of fields oscillating at frequencies too high to imagine. This vision dissolves the boundary between matter and space. The difference between something and nothing becomes one of rhythm, not substance. Matter is vacuum energy arranged in self-reinforcing configurations, balanced like knots in a wave. When these vibrations interact, they exchange quanta, tiny packets of energy, creating the phenomena we observe as forces. To say that we are made of matter is to say that we are made of the vacuum, sculpted into shape by its own resonances. Everything you touch, everything you see, is the vacuum learning to sing in patterns that last. 38. There is no sharp border between matter and empty space. At the atomic scale, the boundary between matter and vacuum blurs. The space inside an atom is almost entirely empty, a vast gulf where electrons dance within probabilistic clouds around a tiny nucleus. Yet this emptiness is not truly void. It's alive with the same fields that permeate all space. The electron's wave functions spread seamlessly into the surrounding vacuum, and the fields of nearby atoms overlap, merging into a continuous whole. This means that the line we draw between an object and its environment is an illusion of scale. The vacuum doesn't end where matter begins, it becomes matter through the interaction of its fields. The solidity we feel is the result of electromagnetic forces repelling one another, not a physical barrier between things and nothingness. In advanced experiments, scientists can even coax atoms to merge their wave functions, forming condensates where the distinction between particle and background disappears entirely. In such states, the vacuum and matter acts as one, a single quantum entity that shifts between forms depending on energy and temperature. The boundary between thing and space is not a wall but a gradient. At its deepest level, reality is seamless. Everything that exists, from the densest star to the faintest breeze, is a rearrangement of the same continuous vacuum fabric. 39 vertissimo. The constants of nature could be fingerprints of our current vacuum. Numbers like the speed of light, the charge of the electron, and the strength of gravity appear fixed and universal. But some physicists suspect that these so-called constants may depend on the state of the vacuum itself. If the vacuum were to shift, if its energy level or structure changed, those constants could change with it. Our entire physical reality might hinge on the particular configuration of the vacuum that the universe happens to occupy. In this view, the constants of nature are not divine numbers, but environmental properties, as arbitrary as the temperature of a room. Different vacuum states could give rise to different universes, each with its own version of physics. We inhabit a region of the vacuum where conditions happen to allow stable atoms, chemistry, and life. Elsewhere, or in other cosmic epochs, the constants might differ, producing realities beyond our comprehension. This idea links cosmology with particle physics, uniting the largest and smallest scales under a single principle. The vacuum sets the rules. The geometry of space, the strength of forces, even the unfolding of time all follow from its configuration. The laws of physics are, in essence, the local dialect of the vacuum's global language. To measure a constant, then, is to take the vacuum's pulse, to listen to the steady rhythm of the universe's current state, knowing that somewhere in the deep past or distant future, the same beat might change. 40. As the universe cooled, the vacuum may have shifted through several phases. In its earliest moments, the universe was unimaginably hot, a turbulent sea of pure energy where forces and particles were indistinguishable. As it expanded and cooled, the vacuum itself underwent a series of phase transitions, like water freezing into ice. Each transition reshaped the fabric of space and altered the behavior of everything within it. At first, the fundamental forces were unified. Then, as the temperature dropped, the symmetry broke, gravity separated, then the strong nuclear force, and eventually electromagnetism and the weak force diverged. Each separation left behind a new vacuum state, lower in energy and richer in structure. These transitions were accompanied by bursts of radiation, waves in space-time, and perhaps even the birth of cosmic defects, relics of the universe's changing geometry. The vacuum we experience today is likely not the final one. It is simply the latest layer in a long cooling process, a snapshot of an evolving field. Deep in its structure might linger echoes of earlier phases, dormant fields or particles that no longer play an active role, but still whisper their presence through subtle effects. To understand the universe's history is to trace the cooling of the vacuum itself, from chaos to order, from perfect symmetry to the diverse, intricate cosmos we now see stretching across the night sky. 41. Precision experiments can detect forces born of pure vacuum. At scales far smaller than the width of a human hair, scientists have built instruments sensitive enough to measure the slightest forces, even those produced by nothing at all. These experiments probe the vacuum directly, detecting minute pressures and energy shifts caused by its fluctuations. When two uncharged metal plates are brought close together, for instance, they attract not because of static electricity, but because the vacuum between them supports fewer quantum modes than the space around them. This phenomenon, known as the Casimir effect, is one of the most elegant confirmations that emptiness is active. The measured force agrees precisely with quantum predictions, leaving no doubt that the vacuum exerts real measurable influence. Similar precision techniques now allow researchers to test whether the vacuum interacts differently near magnetic fields, within superconducting cavities, or under extreme temperatures. Each new measurement refines our understanding of how the vacuum behaves, and perhaps hints at new physics beyond current theories. Tiny deviations from prediction could signal undiscovered particles, hidden dimensions, or subtle shifts in the vacuum's energy density. The smallest experiments may yet reveal the deepest truths about the universe. In a way, these laboratories have become portals into the invisible. Within their ultra-cold chambers and mirror-smooth surfaces, scientists are listening to the faint heartbeat of nothing itself and finding that it is astonishingly loud. 42. Optical cavities reshape light by sculpting the modes of the vacuum. When light is trapped between mirrors, it doesn't simply bounce back and forth. It changes the very vacuum in which it moves. The confined space alters which electromagnetic modes can exist, suppressing some while amplifying others. This reshaped vacuum modifies how photons behave, how they are created, absorbed and emitted. In such optical cavities, the vacuum becomes a tool, an environment that can be tuned and sculpted with precision. Physicists use these cavities to explore the frontier between quantum optics and cosmology. They can simulate conditions near black holes, generate particles from moving mirrors, and even slow the speed of light to a crawl. Every adjustment to the cavity's geometry redefines the vacuum inside, transforming nothing into a laboratory of infinite possibilities. These effects are not theoretical curiosities. They underpin technologies such as lasers, quantum computers, and atomic clocks. By mastering the vacuum's modes, engineers can manipulate energy at its most fundamental level. The emptiness between mirrors becomes a playground for creation, a stage where light and matter perform under the direction of invisible forces. The lesson is clear. The vacuum is not passive. It is a responsive medium that can be molded by design. By learning to shape it, we begin to harness the same principles that sculpted the universe itself. 43. Ultra-cold devices reveal energy that refuses to vanish. At temperatures close to absolute zero, where all thermal motion should cease, scientists still detect a faint jitter, the signature of zero-point energy. This residual motion is not noise from the environment. It is the vacuum's own vibration. Using ultra-cold atoms, superconducting circuits, and trapped ions, researchers have created instruments sensitive enough to detect these quantum whispers directly. Even when every external source of energy is eliminated, the vacuum continues to fluctuate. Atoms in a Bose-Einstein condensate sway minutely, mirrors in optical setups vibrate without any applied force, and quantum sensors pick up correlations that cannot be explained by classical physics. This persistent motion confirms that the vacuum is the ground floor of reality, one that can never be perfectly still. The implications reach beyond the laboratory. These systems allow scientists to explore how quantum mechanics transitions into classical behavior, how decoherence begins, and how energy from the vacuum might be redirected or amplified. They also challenge our intuition about emptiness. How can something with no matter and no temperature still contain so much activity? The answer, increasingly, is that the vacuum is not absence but presence, a field filled with the smallest possible motions, forever beyond the reach of stillness. No matter how cold the universe becomes, the vacuum will continue to hum softly underneath it all. 44. Satellites have distributed quantum entanglement across hundreds of kilometers of near vacuum. One of the greatest tests of the quantum vacuum came not in a laboratory but in orbit. Using satellites, scientists have transmitted entangled photons across hundreds of kilometers through the near-perfect vacuum of space, proving that quantum correlations can survive the emptiness between Earth and sky. This achievement confirmed that the vacuum does not destroy entanglement, it sustains it. In these experiments, twin photons are generated on the ground and sent in opposite directions, one to a mountaintop observatory, the other reflected by satellite back to another receiver. Despite the vast distance and the absence of any medium, their correlation remains perfect. The vacuum, far from being a barrier, acts as a flawless channel for quantum information. This opens a new era of science and technology. Quantum communication networks could someday link entire continents through the vacuum of space, transmitting unbreakable signals carried by entanglement itself. On a deeper level, it shows that the fabric of the vacuum is not fragile but resilient, able to maintain the coherence of delicate quantum states over astronomical distances. The emptiness above our planet, once seen as dead space, is now understood as a living field, silent, stable, and capable of carrying the most subtle connections in existence. 45. Loophole-free tests confirm that quantum correlations persist across empty space. For decades, skeptics of quantum mechanics argued that entanglement might be an illusion caused by hidden variables or experimental flaws, but in recent years, loophole-free experiments have settled the debate. By closing every possible gap, detector inefficiency, communication delay, and local influence, physicists have demonstrated beyond doubt that entanglement is real and that it persists even across vast stretches of empty space. These tests show that the quantum vacuum does not separate objects, it unites them. Pairs of photons, to electrons, or even atoms can remain correlated through the vacuum itself, as if sharing an invisible thread that transcends distance. The results violate classical ideas of locality and force us to accept that reality is not built from isolated parts, but from a single interconnected field. Each new experiment extends the reach of this phenomenon, from laboratories to satellites, from nanometers to kilometers. The vacuum remains transparent to entanglement, preserving coherence where ordinary matter would introduce noise and loss. It's as if the universe's most silent regions are also its most faithful custodians of connection. These findings reshape our view of space. Emptiness is not separation, it is continuity. The vacuum is not a wall between objects, but the medium through which they remain one. 46. The flow of time may depend on the dynamics of the vacuum. We tend to think of time as an independent river, flowing relentlessly from past to future, carrying everything with it. But some physicists now suspect that time's arrow might not exist apart from the behavior of the vacuum itself. In this view, what we perceive as the passage of time could emerge from the continual fluctuations of the quantum fields that fill space. Each vibration, each exchange of virtual particles sets the tempo of the universe's hidden clock. If the vacuum's dynamics were ever to change, if its fluctuations were to slow or freeze, time as we know it might falter or even stop. This idea connects the origin of time's direction to entropy, to the way vacuum energy flows from less organized states to more complex configurations. The expansion of the universe, the fading of stars, even our own memories unfold in harmony with that flow. Time is not external to the vacuum, it is born from it. The possibility that time emerges from the vacuum also offers an explanation for its uniformity. Everywhere we look, the cosmos seems to share the same rhythm. Seconds tick the same in galaxies billions of light-years apart. This could be because all regions of space are synchronized through the same underlying field, the same ceaseless quantum beat. In this sense, time is not a stage upon which the universe performs, but a vibration of the performance itself. The ticking of clocks, the unfolding of moments, the growth of complexity, all may be reflections of the same deep eternal pulse that hums beneath reality. 47. If the vacuum ever froze completely, time itself might stop. Imagine the entire universe gradually cooling until even the faintest quantum motion ceased. No ripples, no fluctuations, no virtual particles, a perfect stillness. According to our best theories, such a state is impossible. But if it could exist, time would lose all meaning. for time is not a thing in itself. It is the measure of change, and change is driven by energy. If the vacuum were truly frozen, if its zero-point motion somehow halted, then every process in the universe would freeze with it. This isn't just a poetic speculation. The equations of quantum field theory imply that without fluctuations, there would be no events to separate before from after. Entropy would no longer increase, clocks would cease to tick, and causality would dissolve. The very concept of history would evaporate into an eternal static void. Some cosmologists even wonder whether the universe could asymptotically approach such a state in the far future. As galaxies drift apart and stars burn out, the vacuum energy might dominate completely, leaving nothing but cold expansion and a faint hum of residual motion. In that final age, time would slow almost to nothing, stretched thin across an ever-widening emptiness. Perhaps that is how existence ends, not in fire or collapse, but in silence. The day the vacuum stops vibrating would be the day the universe forgets how to move. 48. Apparent randomness may hide coded structure in the vacuum. Quantum mechanics teaches that the behavior of particles is fundamentally probabilistic, that outcomes can only be predicted as chances, not certainties. Yet some researchers wonder whether this apparent randomness conceals a hidden order encoded within the vacuum itself. Could the fluctuations we see as noise actually follow deeper patterns, too subtle or complex for current mathematics to reveal? The vacuum is, after all, not chaos, but a system governed by precise laws. Its fluctuations obey statistical distributions that remain stable across all scales, suggesting that there is method beneath the unpredictability. Some physicists propose that the vacuum may store information holographically, weaving deterministic structure into what appears to be random motion. If that is true, then the universe's uncertainty may be an illusion born of limited perspective. Every particle's behavior, every quantum event, could be part of a vast, interconnected algorithm, a cosmic code written in the oscillations of empty space. What we interpret as chance may be the compressed expression of rules so intricate that they appear disordered. Even without definitive proof, this idea transforms how we see randomness. The vacuum may not be the birthplace of chaos, but its architect, a realm where apparent disorder conceals a hidden symmetry, quietly shaping the unfolding of reality. 49. At the Planck scale, space becomes a frothing quantum foam. If we could shrink ourselves to sizes far smaller than an atom, past quarks, past strings, down to the Planck length and 100 billion times smaller than a proton, space itself would lose meaning. Geometry would dissolve into turbulence. The vacuum would no longer appear smooth but would churn like a stormy ocean, with bubbles of space-time constantly forming and collapsing. This is the realm of quantum foam where gravity and quantum mechanics merge into one wild dance. At this scale, distances, times, and even causality fluctuate. Tiny wormholes may open and close, connecting points of space for fleeting instants before vanishing again. Energy and curvature fluctuate so violently that up and down cease to exist. The vacuum becomes a network of ever-changing connections, a dynamic web that underlies all higher forms of order. Physicists suspect that this chaotic sea may give rise to the smooth spacetime we experience, just as the rough motion of water molecules produces the calm surface of a lake when viewed from afar. Space as we know it could be an emergent property of this deeper quantum turbulence. If so, then the vacuum is not simply the foundation of reality, it is reality in its rawest form. Every calm expanse of sky, every beam of starlight, is built atop a microscopic tempest that never stops raging beneath our awareness. 50. Space and time might not be fundamental, but emergent. We are taught to think of space and time as the ultimate backdrop of the universe, the grid on which everything happens. But a growing body of theory suggests the opposite, that space and time themselves may arise from deeper principles rooted in the quantum vacuum. In this view, what we experience as distance or duration could be emergent properties of underlying relationships among entangled quantum states. If true, then the vacuum is not something within space, it is what space is made of. The geometry of the universe would emerge from the connectivity of quantum information, from how the vacuum's microstates are linked and correlated. Time, likewise, could be a measure of how these correlations evolve, rather than a pre-existing flow. This concept explains why the universe appears smooth on large scales even though it's composed of discrete quantum events. The geometry we perceive is an average of vast microscopic fluctuations, stabilized by entanglement. Reality becomes a holographic network of connections, constantly updating itself from within. To grasp this is to see that the vacuum is not contained by space, it creates it. The distances we measure, the seconds we count, and the motion of galaxies are all consequences of an invisible architecture, one built not from substance but from relationship. 51. Biological systems could subtly resonate with vacuum fluctuations. Though it may sound speculative, some physicists and biologists have begun to explore how living systems might interact with the quantum vacuum. Every molecule, every neuron, every cell that exists within and constantly exchanges energy with this background field. At small scales, the fluctuations of the vacuum influence chemical reactions, molecular vibrations, and even electron transfers, processes essential to life itself. Quantum coherence, once thought impossible in warm biological environments, has now been observed in photosynthetic complexes and even in certain neural processes. These delicate correlations may persist because the vacuum provides a stabilizing medium, a sea of fluctuations that synchronizes the rhythm of quantum events. It is as though life has learned to dance in harmony with the tremors of emptiness. While this doesn't mean consciousness or biology controls the vacuum, it does suggest that the two are intertwined more deeply than once believed. Life is not separate from the physical world, it is a sophisticated manifestation of it. The same fields that govern particle physics may also whisper in the quantum machinery of the cell. To exist is to participate in the vacuum's endless vibration. Every heartbeat, every thought, every breath is accompanied by the silent resonance of the field that sustains both stars and synapses alike. 52. Molecular bonds form within the restless sea of background energy. When two atoms bond to form a molecule, the interaction seems purely chemical. Electrons shared, energy minimized, stability achieved. But beneath that chemistry lies the quantum vacuum, shaping the forces that hold everything together. The electromagnetic fields of atoms interact not in isolation, but through a background already alive with motion. The distribution of vacuum fluctuations modifies how electrons orbit, how potential wells align, and even how energy levels split. This means that the vacuum doesn't merely surround matter, it sculpts it. The shape of molecules, the precision of spectra, and the fine balance between attraction and repulsion all depend on how the vacuum mediates electromagnetic fields. Quantum electrodynamics shows that these subtle corrections are measurable. The Lamb shift, van der Waals forces, and Casimir-Polder effects all owe their existence to the restless activity of empty space. When you look at a drop of water, you're seeing the product of these interactions, a trillion molecular partnerships, each stabilized by forces that arise from the vacuum's invisible hand. Every chemical bond is in essence a negotiation between matter and the background field that binds it. Thus, the structure of every living cell, every crystal, every cloud is a directed chirurgic expression of how the vacuum behaves. Even the gentlest curve of a molecule's geometry is written by the pieped tremor of nothingness beneath it. 53. Chemical reaction rates can shift by altering vacuum modes. The idea that chemical reactions could be influenced by manipulating the vacuum might sound fantastical, yet experiments have begun to demonstrate just that. When molecules are placed inside optical cavities, mirrored environments that confine light and reshape the vacuum's electromagnetic modes, their reaction rates can change dramatically. Bonds form or break more quickly, activation energies shift, and entirely new reaction pathways appear. What's happening is that the vacuum inside the cavity has been restructured. The allowed field modes are altered, changing how the molecules exchange energy with their surroundings. Even when no light is injected, the vacuum itself mediates a new pattern of interaction. It's a striking reminder that empty space is an active ingredient in chemistry. This emerging field, known as cavity quantum chemistry, may one day allow scientists to control reactions not just by adjusting temperature or catalysts, but by engineering the vacuum environment itself. The chemistry of the future might depend as much on the design of space as on the design of molecules. Each discovery in this area blurs the boundary between quantum physics and life's complexity. The vacuum is no longer a silent spectator, it is a collaborator, quietly shaping the rhythm of matter's transformations. 54. Superconductors and superfluids are macroscopic echoes of ordered fields. When certain materials are cooled to near absolute of zero, something extraordinary happens. Their internal order aligns so perfectly that resistance vanishes. Electrons flow without friction, fluids move without viscosity, and energy circulates in eternal loops. These phenomena, superconductivity and superfluidity, are not merely low-temperature curiosities. They are glimpses into how fields behave when noise and disorder are stripped away. In these systems, the vacuum of the material's quantum field takes on a coherent state. Countless particles act as one, sharing a single quantum wave function that extends over macroscopic distances. This unified state mimics, on a smaller scale, the coherence of the universal vacuum itself. It's as though the material momentarily remembers the symmetry and harmony of the early universe. Such ordered fields reveal that coherence is not rare. It is the natural tendency of the quantum world when left undisturbed. The vacuum we inhabit might be a similarly coherent state on a grander level, stabilized by the interplay of all fundamental forces. In the hum of a superconductor or the whisper of a superfluid, we catch an echo of the cosmic order, the same symmetry that the vacuum itself has maintained since time began. 55. Every reference frame is defined relative to the omnipresent fields. In classical physics, motion is measured relative to space itself, an abstract backdrop. But in the quantum world, there is no empty backdrop. Every region of the universe is filled with fields that define orientation, energy, and motion. Whether we move or remain still is always relative to the vacuum structure, not to some external void. The electromagnetic, Higgs, and gravitational fields permeate all of existence, providing the scaffolding upon which all reference frames are built. When a particle accelerates, it disturbs these fields, leaving traces that define direction and momentum. Even the inertial frames described by Einstein's relativity are shaped by this unseen lattice, the vacuum's ever-present foundation. This realization erases the distinction between something and nothing. Motion through space is, in truth, interaction with the vacuum. The resistance we call inertia, the constant of the speed of light, and the shape of space-time itself all derive from the properties of these omnipresent fields. To move anywhere in the universe is to move within this invisible framework, a silent, universal ocean that defines what motion means. Even when we feel weightless, we are never free from its influence. The vacuum is our only true frame of reference. 56. Zero-point energy has inspired dreams of limitless power. From the moment scientists realized that even empty space holds energy, imaginations leapt ahead to a breathtaking possibility. Could that energy be harnessed? After all, if every cubic centimeter of the vacuum contains an immense amount of zero-point energy, then the universe is saturated with potential. Some estimates suggest that if even a fraction of this energy could be tapped, a single roomful of space could power civilization for millennia. It is the ultimate seduction, infinite energy from nothing. Yet the deeper our understanding grows, the clearer it becomes that the vacuum is not a resource waiting to be mined, but a delicate equilibrium. The zero-point field is balanced perfectly. Its fluctuations average to stability, not abundance. To extract energy would mean disrupting the structure that defines reality itself. For now, all theoretical attempts, from speculative quantum drives to vacuum resonance reactors, run up against fundamental conservation laws that prevent such extraction. Still, the dream persists, not as a fantasy of free energy, but as a philosophical reflection, the recognition that power is already everywhere, invisible but real. The vacuum is the ultimate battery, one that cannot be drained because it is the baseline of all energy. Perhaps the real revolution is not to exploit it but to understand it, to learn how the universe sustains motion and creation from the constant hum of zero-point balance. In the end, the pursuit of vacuum energy reveals more about human longing than about physics. Our desire to grasp infinite power mirrors the vacuum's own paradox, limitless potential that remains forever just beyond reach. 57. Nanoscale engineering can shape the strength of vacuum forces. At the microscopic scale, emptiness becomes a tool. Engineers have learned that by shaping surfaces at the nanometer level, sculpting ridges, patterns, and gaps thinner than a wavelength of light, they can control how the vacuum behaves between them. These tiny structures modify the quantum modes of the electromagnetic field, changing how Casimir forces act. The result is a new kind of engineering, one that designs not matter, but the space between matter. By manipulating geometry, scientists can make the Casimir force attractive, repulsive, or nearly vanish. This control opens possibilities for ultra-sensitive sensors, frictionless bearings, and quantum devices immune to stiction. The sticking caused by microscopic attraction. In these realms, the vacuum is as tangible as any material, shaping how objects move and interact. The implications are profound. Humanity has begun to sculpt the vacuum itself, bending its invisible currents to our will. Just as engineers once learned to channel electricity, we are now learning to shape the energy of nothingness. Each refinement of a surface, each reconfiguration of light's allowed modes, is a small act of mastery over the most fundamental field there is. In these silent laboratories, humans have started to do what nature has done since the dawn of time: use geometry to guide the vacuum's dance, creating structure from the formless sea that underlies all existence. 58. Metamaterials can mold the electromagnetic vacuum itself. Metamaterials, artificial composites designed with patterns smaller than the wavelength of light, have unlocked astonishing abilities. They can bend light backward, render objects nearly invisible, and manipulate electromagnetic waves in ways nature never intended. What's even more remarkable is that they achieve this not by changing the material itself, but by shaping how the vacuum interacts with it. In a metamaterial, the arrangement of tiny structures controls how the vacuum's electromagnetic modes behave. Light, magnetism, and even the propagation of virtual photons adjust accordingly. In essence, metamaterials rewrite the local rules of the vacuum, creating pockets of altered optical reality. The space inside and around them ceases to behave like ordinary emptiness. It becomes a tailored environment with its own geometry of interaction. This technology hints at a deeper future. If we can design materials that shape the vacuum's behavior, perhaps we can one day control the flow of energy and information at the most fundamental level. The manipulation of light and field could lead to unprecedented forms of communication, computation, and sensing. The metamaterial revolution shows that the vacuum is not immutable. It is a medium, flexible, responsive, and sculptable. By learning its language, humanity has begun to converse with the very foundation of physics. 59. Some spacecraft concepts imagine propulsion by manipulating the vacuum. The idea of a ship that moves without fuel, propelled only by interaction with the quantum vacuum, has long captured the imagination of engineers and dreamers alike. Could a craft somehow push against the vacuum's fluctuations, using the sea of virtual particles as an invisible reaction mass? The concept, sometimes called quantum vacuum propulsion, remains speculative, yet it challenges our intuition about what motion requires. In classical mechanics, movement depends on expelling mass. Thrust comes from action and reaction. But in the quantum view, the vacuum itself is filled with energy and fields that could, in theory, be disturbed. Some proposals suggest that manipulating the local geometry of the vacuum through electromagnetic fields or cavity oscillations might produce a tiny net force. Thus far, no experiment has confirmed this, and most physicists remain skeptical, arguing that the vacuum's symmetry forbids any net propulsion without violating conservation laws. Still, the question persists because it probes the border between physics as we know it and physics as it might become. The dream of moving by shaping space itself is not mere science fiction. It's an expression of our growing understanding that the vacuum is an active participant in motion. If propulsion through vacuum engineering ever becomes real, it would mark humanity's first conversation with the universe's most silent engine, travelling not through space, but with it. 60. Quantum sensors turn vacuum noise into useful signals. Noise is usually the enemy of measurement, a source of error to be reduced or eliminated. But in quantum physics, even noise holds information. The vacuum's fluctuations, once thought to be random background hiss, can be transformed into a tool of extraordinary precision. Quantum sensors, devices that operate at the edge of uncertainty, exploit these fluctuations to detect forces, fields, and displacements with sensitivity beyond classical limits. By preparing particles or photons in special states that interact predictably with the vacuum's noise, these sensors extract meaning from chaos. Gravitational wave detectors, for instance, rely on squeezed light in which the vacuum's uncertainty is redistributed to enhance precision in one variable at the expense of another. The result is an instrument that listens to the faint tremors of space-time itself. These technologies are proof that the vacuum is not an obstacle to knowledge, but its partner. The same uncertainty that limits measurement also enables it, offering a reservoir of quantum effects that can be tuned and amplified. In the hands of skilled physicists, even emptiness becomes a source of information. We are learning to hear the vacuum's static as music, to extract from its hum the hidden patterns that reveal the deepest workings of the universe. 61. Nothingness may be the most creative element in nature. It is tempting to think of creation as the act of adding, of producing more from less. But the universe suggests another story, that creation arises not from abundance but from emptiness. The vacuum, which we once imagined as pure absence, turns out to be the source of everything. It is an inexhaustible well of energy and form, constantly fluctuating, forever on the edge of becoming. Every particle, every field, every beam of light was born from this background of potential. The Big Bang itself may have been a quantum fluctuation in the vacuum, a spontaneous bloom of existence from balance. Far from being a lifeless void, the vacuum is the engine of transformation, the stage on which matter and energy endlessly appear and vanish. This realization reverses our intuition. The vacuum is not what remains when everything is removed. It is what must exist before anything can appear. It is the fertile ground of the cosmos, invisible, quiet, and infinitely productive. If we look deeply enough, we find that nothing is not the opposite of something. It is the womb from which something continuously emerges. The universe is the vacuum's way of creating meaning. 62. Information might be preserved through hidden degrees of the vacuum. The principle of information conservation, the idea that no information in the universe is ever truly lost, is one of the cornerstones of physics. Yet when matter falls into a black hole or energy dissipates into heat, where does that information go? One compelling answer lies in the vacuum itself. It may store lost information in subtle quantum correlations, hidden within its vast network of entangled states. This notion resolves the long-standing information paradox raised by Hawking radiation. If the vacuum carries the missing data, then nothing ever truly vanishes, it merely changes form, encoded in patterns too complex for us to read. In this sense, the vacuum behaves like a cosmic archive, preserving the complete history of interactions across time and space. Some researchers propose that these hidden degrees of freedom operate at the Planck scale, far below current experimental reach, where the geometry of space-time itself becomes quantized. There, information could be woven directly into the structure of the vacuum, not stored in bits, but in relationships. If so, then every cubic centimeter of empty space contains the memory of everything that has ever happened within it. The vacuum would be the universe's final witness, keeping perfect record of all creation in the quiet language of quantum entanglement. 63. The birth of the universe may have been a single vibration of nothingness. Before there was matter, before there was light, there was the vacuum, uniform, featureless, yet restless. Quantum theory tells us that even perfect stillness cannot last. Fluctuations are inevitable. Perhaps, in one such fluctuation, the vacuum briefly surged, its energy spiking into an unstable configuration. That surge expanded, releasing energy, creating space and time themselves. In that instant, nothing became everything. This vision of the universe's origin doesn't require an external cause or a divine spark. It arises naturally from the laws of physics. The vacuum, in its eternal restlessness, occasionally produces bubbles of reality. One of those bubbles expanded and cooled into the universe we now inhabit. In this view, existence is not an exception to the vacuum. It is one of its ordinary behaviors. The Big Bang, then, may have been less an explosion and more a transformation. The vacuum shifting into a higher energy state and then cascading down, converting potential into matter and radiation. Space grew, time flowed, and from the hum of the vacuum, structure emerged. It is an origin story that humbles and inspires. The universe did not arise from emptiness, but from the necessity that even emptiness must move. The first vibration of nothingness became the song of everything. 64. The end of the universe could be the calm return to its lowest vacuum state. If the birth of the cosmos was a surge of vacuum energy, its death may be the quiet settling back into equilibrium. Over trillions of years, stars will exhaust their fuel, galaxies will fade and black holes will evaporate. The expansion of space will continue, driven by the same vacuum energy that once gave it life. Eventually, only a thin soup of particles and radiation will remain, thinning ever further as time drifts toward infinity. In that far future, if the vacuum has a true ground state lower than today's, the universe may undergo one final transformation, a transition into its ultimate calm. Space would relax into perfect uniformity, free of matter, radiation and curvature. The last traces of entropy would dissolve. Time itself might lose direction, its arrow extinguished as all processes cease. This is not an apocalypse, but a homecoming. The universe would not end violently, but fade peacefully into stillness, returning to the state from which it began. The vacuum would remain quiet, eternal, balanced. In that silence, the story of existence would come full circle. The same field that once sparked creation would cradle its ashes, holding forever the memory of what once was. 65. Beneath our known vacuum could lie deeper strata of reality. The vacuum we observe, with its zero-point energy, its fields, its structure, may not be the ultimate ground of existence. It might simply be one layer of a deeper hierarchy. Just as matter is composed of atoms and atoms of subatomic particles, the vacuum itself could have constituents, hidden layers of physics that operate at energies far beyond our reach. Theories of quantum gravity, string theory, and loop cosmology all hint at this possibility. Beneath the quantum fields that define our reality might lie more fundamental entities, vibrating strings, spin networks, or even pre-geometric structures. Each would give rise to the vacuum we know in the same way that water molecules give rise to the fluid surface of the sea. If true, then our entire universe is a phase, a state of matter in a much larger system. Deeper vacua might exist with different rules, capable of birthing new universes through transitions much like cosmic inflation. The nothing we call empty space could be a thin membrane floating atop an ocean without bottom. To seek what lies beneath the vacuum is to ask the oldest question in science: what is the universe made of? The closer we look, the clearer it becomes. The answer is not things, but layers of being nested within one another, all the way down to the unfathomable. 66. Space-time points might actually be threads of entanglement. What if the points of space themselves, so the very coordinates we use to describe position, are not fundamental but woven from quantum relationships? According to emerging theories in quantum gravity, space-time may be built from patterns of entanglement, the invisible bonds that link particles through the vacuum. Each point is not an isolated location, but a junction of quantum connections, a thread in an infinite tapestry. In this view, the smooth geometry we experience is the large-scale limit of a deeper quantum network. The closer two regions are in space, the more entangled their underlying quantum states are. Distance becomes a measure of correlation. Geometry is the shadow cast by information. Where entanglement is dense, space feels continuous. Where it weakens, space itself begins to fray. This idea replaces the old notion of space-time as a passive container with the living web of relationships. Matter and gravity arise not on top of this network, but from it. The very shape of the universe, its curves, its dimensions, its continuity, emerges from the way the vacuum's microstates are woven together. If true, then reality is not made of points, but of connections. The universe exists not because there is something in space, but because space is the totality of everything that connects. To understand the vacuum is to read the pattern that holds existence together. 67. The arrow of time could depend on how vacuum energy flows. Time's arrow, the relentless direction from past to future, remains one of the universe's great mysteries. The laws of physics themselves don't prefer one direction over the other, yet our world clearly does. One possible answer lies in the flow of vacuum energy. The quantum fields that fill space are not static. They exchange energy with matter, radiation, and geometry in subtle ways. That continual redistribution may define the orientation of time itself. If the vacuum's fluctuations were perfectly symmetrical, time might have no preferred direction, but they are not. The early universe began in a state of lower entropy, and the vacuum's energy has been spreading and relaxing ever since. This slow drift toward equilibrium could be the deep mechanism behind the arrow of time, the reason why we remember the past but not the future, why stars burn, and why decay outweighs creation. Seen from this angle, time's flow is not a property of clocks or motion, but of the vacuum's evolution. It is the unfolding of the universe's energy landscape as the vacuum continually adjusts toward balance. Even the decay of unstable particles and the redshift of light over cosmic distances reflect this same process, the vacuum relaxing, cooling, and expanding. If that's the case, then every second we experience is a small symptom of the vacuum's ongoing exhalation. Time flows because the universe is still breathing out. 68. Every measured particle property is adjusted by vacuum corrections. When physicists calculate the mass, charge, or magnetic moment of a particle, they never find a simple, clean number. Instead, they discover layers of corrections, tiny adjustments produced by the particle's interaction with the vacuum. These corrections, often computed using Feynman diagrams, represent all the ways virtual particles can emerge and vanish around a particle, changing its properties slightly. For example, the electron's magnetic moment, how it responds to a magnetic field, differs minutely from the value predicted by the simplest equations. That discrepancy, called the anomalous magnetic moment, arises entirely from vacuum fluctuations. Quantum electrodynamics predicts it with astonishing accuracy, matching experiments to more than 10 decimal places. Every particle in nature carries such corrections, signatures of its dialogue with the vacuum sea. This constant adjustment reveals that nothing exists in isolation. A particle's identity is not fixed. It's the result of an endless conversation between itself and the quantum fields around it. The vacuum shapes every measurable property, mass, charge, even lifetime, through its perpetual feedback. In short, what we call a particle is not a self-contained object, but a process. It is the visible crest of an invisible exchange with the vacuum, always shifting, always refined by the background energy of existence. 69. The vacuum may unite all forces at unimaginably high energies. At the energies we can observe, the universe's forces seem distinct. Gravity governs the large, electromagnetism governs the charged, and the nuclear forces rule the subatomic. But as we probe deeper into the vacuum structure, a pattern emerges. The closer we approach the conditions of the early universe, the more these forces begin to converge. The vacuum may be the unifying medium through which all interactions ultimately blend into one. In theories of grand unification, the differences among forces arise because the vacuum is in a broken symmetry state, a cooled, crystallized version of a once unified field. At higher energies, closer to those of the Big Bang, the symmetry would be restored. The vacuum would behave differently, merging separate homod fields into a single fundamental interaction. Gravity might even join the others, revealing that all forces are variations on one underlying geometry. This is more than a mathematical dream. Experiments in particle accelerators already show hints of convergence. The strengths of the forces change subtly with energy, guided by the structure of the vacuum's quantum corrections. Those trajectories almost meet, suggesting that at an energy billions of times higher than any we can produce, unity waits. The quest for that unity is a quest to understand the vacuum's deepest nature. For when the forces merge, so too will our understanding of space, time, matter, and energy, all born from a single boundless field. 70. Geometry itself could be the statistical average of vacuum fluctuations. When we look at the world, we see smooth space and continuous time, but at the smallest scales, space is anything but smooth. It seethes with quantum fluctuations that distort its geometry moment by moment. Some physicists propose that the geometry we observe is not fundamental at all, but an average outcome of these fluctuations. In other words, space-time's shape is statistical, the macroscopic calm of microscopic chaos. This picture fits with what we know of the quantum foam at the Planck scale. There, space-time bubbles and collapses continuously, creating transient curvatures and wormholes. On larger scales, those violent changes average out into the smooth geometry described by Einstein's relativity. The fabric of space is not a continuous cloth but a blurred mosaic of quantum events. This interpretation bridges quantum mechanics and general relativity without forcing them into conflict. The vacuum becomes the source of curvature, and geometry becomes an emergent pattern, the arithmetic mean of the vacuum's endless dance. Space is stable not because it is static, but because its fluctuations are balanced in statistical harmony. If geometry is an average, then the universe itself is a kind of illusion, a long-exposure photograph of the vacuum's motion, smooth only because we are too slow to see the turbulence beneath. 71. The Scharnhorst effect suggests light can travel slightly faster between plates. In the early 1990s, physicists exploring the Casimir effect made a startling theoretical prediction. Between two closely spaced metal plates, light might travel ever so slightly faster than it does in normal vacuum. This phenomenon, known as the Scharnhorst effect, arises because the plates suppress certain vacuum fluctuations, reducing the number of virtual particles that can interact with the photons passing between them. With fewer disturbances, light experiences marginally less resistance from the vacuum. The predicted difference is extraordinarily tiny, far beyond any current ability to measure, but its meaning is profound. It shows that the speed of light is not an untouchable constant handed down from the heavens, but a property of the vacuum itself. Change the vacuum, and you change the rules. This insight deepens our appreciation of how intertwined light and emptiness truly are. Photons are not independent travelers. They are disturbances of the electromagnetic field moving through an ocean that can be tuned by geometry and material boundaries. The vacuum defines their pace, their direction, even their identity. Though the Scharnhorst effect will likely never be exploited for faster-than-light travel, it remains a fascinating reminder. The ultimate speed limit of the universe is set not by an abstract number, but by the living character of the vacuum that fills it. 72. Radiative corrections alter magnetic moments through vacuum loops. The magnetic properties of particles, such as the electron and muon, are among the most precisely measured quantities in physics, and yet even they are not what simple theory predicts. The reason lies in the vacuum's loops, countless virtual photons, electrons, and positrons that continuously pop in and out of existence around every charged particle. These loops slightly modify the particle's magnetic field, producing a small but measurable deviation from the classical value. This effect, known as the anomalous magnetic moment, is one of quantum electrodynamics' greatest triumphs. Theoretical predictions match experimental measurements to more than 1 part in a trillion, confirming that the vacuum's loops are real and measurable. But the same precision also exposes potential cracks in our understanding. The muon's magnetic moment, for instance, appears to deviate from theory just enough to suggest undiscovered physics hiding in the vacuum. These tiny discrepancies may hold the keys to deeper layers of reality. They might hint at new particles, hidden forces, or even subtle changes in the vacuum's structure. The loops that distort magnetic fields could be gateways to phenomena beyond the standard model. Each experiment is a dialogue with emptiness, a way of asking the vacuum to reveal whether it is truly complete, or whether it still hides secrets in its endless self-interactions. 73. The Unruh effect makes the vacuum appear warm to an accelerating observer. According to relativity, motion changes how we perceive space and time, but quantum physics adds a twist. Motion also changes how we perceive emptiness. An observer at rest in a vacuum sees nothing, no particles, no heat. Yet an observer accelerating through that same vacuum will detect a faint glow of radiation, as if space itself has warmed up. This is the Unruh effect, a phenomenon that ties together acceleration, temperature, and the quantum nature of the vacuum. The effect arises because its acceleration skews the balance of vacuum fluctuations. To the moving observer, virtual particles and antiparticles no longer appear symmetrically. The imbalance manifests as real photons, a thermal bath with a temperature proportional to acceleration. In essence, motion through the vacuum creates heat. This insight unites thermodynamics, relativity, and quantum quantum theory in a single elegant statement. The vacuum is not absolute, but observer-dependent. What is empty for one observer may be filled with radiation for another. Reality, even at its most fundamental, depends on perspective. The Unruh effect has never been directly measured. The accelerations required are extreme, but its implications ripple through black hole physics, cosmology, and the philosophy of observation. It shows that warmth and motion are woven into the same invisible fabric, the trembling vacuum that defines what nothing means. 74. The dynamic Casimir effect turns moving mirrors into sources of light. In classical physics, a mirror only reflects existing light. But in quantum physics, even a mirror in perfect darkness can create light, if it moves fast enough. The dynamic Casimir effect occurs when a mirror oscillates at relativistic speeds, causing the boundary conditions of the vacuum to change so rapidly that virtual photons are promoted into real ones. The mirror, in effect, pulls light out of nothing. This phenomenon has been demonstrated experimentally using superconducting circuits that simulate moving mirrors at gigahertz frequencies. The result is unmistakable. Measurable microwave photons appear from the vacuum created solely by motion. Energy is not conjured from nowhere. It comes from the kinetic energy of the mirror, converted into radiation through its interaction with the quantum field. The dynamic Casimir effect is more than a curiosity. It proves that the vacuum can be stimulated, that changing its boundaries or motion alters its energy content. It blurs the distinction between creation and conversion, showing that light and geometry are interchangeable aspects of the same process. Every time a boundary moves, the vacuum responds. Every time space is reshaped, light is born. It is as if the universe cannot resist turning motion into illumination. 75. Extreme magnetic fields can make the vacuum behave like a crystal. When magnetic fields become unimaginably strong and billions of times greater than those on Earth, like near neutron stars and magnetars, the vacuum itself changes. It becomes birefringent, meaning it bends light differently depending on polarization, much like a crystal splits light into colors. This vacuum birefringence occurs because the intense magnetic field polarizes the virtual particles that constantly flicker in and out of existence. In these conditions, empty space stops being empty. The magnetic field aligns the ephemeral pairs of electrons and positrons, creating a preferred direction in the vacuum. Light traveling through such regions experiences the vacuum not as uniform but as a structured medium, one that refracts, filters, and slows photons based on their polarization. Astronomers have observed hints of this effect in the polarized light from distant magnetars, suggesting that the vacuum truly changes character under such conditions. The phenomenon provides a rare glimpse into quantum electrodynamics at its most extreme, where the vacuum becomes a material with measurable optical properties. It is a striking image, even in the heart of the cosmos, where no matter remains, the vacuum itself can crystallize under the right forces. Space is not an empty void, but a shape-shifting medium, a chameleon that transforms when pushed to its limits. 76. Powerful electric fields can spark particle pairs out of the vacuum. When an electric field becomes extraordinarily strong, on the order of 10 to the 18th power volts per meter, it can literally rip apart the fabric of empty space. At that intensity, the field's energy density becomes sufficient to pull virtual electron-positron pairs into reality, preventing them from recombining. This process, known as Schwinger pair production, turns pure field energy into matter. The phenomenon has yet to be achieved in the laboratory, though upcoming high-power laser systems are approaching the threshold. In theory, it represents one of the most direct ways to witness creation from the vacuum, energy converting directly into mass, as allowed by Einstein's equation E equals mc squared. No particle collisions are required. The field itself provides the energy needed to bring new particles into being. This mechanism shows that the vacuum is not inert but elastic. Under sufficient stress, it yields, forming matter the way a stretched membrane might form bubbles. It is the quantum equivalent of lightning in a storm that never ends. The process also plays a role in cosmic phenomena, such as near pulsars and black holes, where immense fields routinely reach these critical levels. To watch the vacuum erupt into pairs of light and matter would be to see the universe's most fundamental transformation, the birth of substance from the tension of nothingness. 77. Near massive objects, the refractive index of the vacuum subtly changes. Einstein taught us that gravity bends light by curving space-time, but quantum physics adds a finer detail. Gravity also changes how the vacuum itself behaves. Near very massive bodies, such as black holes or neutron stars, the density of virtual particles increases slightly due to gravitational compression. This alters the vacuum's refractive index, a measure of how light propagates through it. The effect is minute but conceptually profound. It means that the vacuum around a massive object behaves a bit like glass with a variable thickness, slowing and bending light not only because of geometry, but because the quantum fields themselves respond to gravity. Space, in other words, is optically active. This quantum lensing adds a Nahovleveil layer to our understanding of how the cosmos works. It suggests that gravity doesn't merely tell light where to go, it changes the medium through which light travels. The vacuum itself becomes part of the gravitational machinery, its fluctuating fields adjusting to curvature like ripples conforming to the shape of a wave. Even the most silent emptiness then participates in the drama of gravity. The vacuum is not an observer of cosmic motion, but a co-author, its texture warping in response to mass and energy. 78. The state of the vacuum depends on who and how you're observing. The vacuum, contrary to intuition, is not the same for everyone. An astronaut floating freely in deep space experiences a vacuum that appears completely cold and empty, but an astronaut accelerating or hovering near a black hole perceives warmth, radiation streaming from what others still call nothing. This observer dependence, revealed by the Unruh and Hawking effects, shows that emptiness is relative. The key lies in how motion and gravity warp perception. The quantum fields that define the vacuum oscillate differently depending on one's trajectory through space-time. Two observers, moving differently, slice the same field in different ways, disagreeing on what counts as particles and what counts as vacuum. To one, space is silent, to the other it glows. This relativity of emptiness challenges our deepest assumptions about reality. There is no single absolute nothingness, only a set of perspectives shaped by motion, gravity, and time. The vacuum, like the universe itself, is subjective. What we call reality is therefore woven not only from the properties of space, but from the experience of those who move through it. The vacuum does not exist without observers. It changes with them, proving that observation is not an afterthought of physics, but part of its foundation. When we gaze into the emptiness of space, we imagine silence. But what lies beyond that silence is the pulse of everything, the invisible engine that never sleeps. The quantum vacuum is not the absence of reality. It is the substance of it, breathing quietly beneath galaxies, beneath atoms, beneath our very thoughts. Every photon, every whisper of gravity, every heartbeat of existence rises and falls upon that sea. Perhaps that is why the night sky feels so infinite, because it's not empty at all, but overflowing with invisible creation. As you drift now into rest, remember, the universe is still moving, still humming, still alive within the stillness. You are part of that same eternal vibration, a ripple on the calm ocean of the quantum vacuum itself. If you enjoyed this journey, don't forget to like the video, comment, and subscribe to our channel. With your support, we can make this community of science and discovery even bigger. Share your ideas with us, because it's always more exciting to explore the unknown together. As Carl Sagan said, reality may be much stranger than we realize. Science is the most powerful way to understand this strangeness.